as I said, I just focus on the giving the idea. So let me apologize that. So I skip every prior knowledge. We don't get into the details of the algorithm or detail of the program. I just give the idea by using the showcases. And so the main message is, through the talk, please try to explore the utility of the machine learning in your own research fields. So this is a message. So this is an image of today's topic. So for example, let's consider just a simple rounding control. Then, without considering the aerodynamical effect, and by applying the simple landing control, so we can't achieve the smooth landing, and it makes the robot might be unstable near the ground because of the counter effect, counter wind. So, but if we apply the learning method, which I introduce now, so we can achieve the smooth landing. This is the image of today's talk. Okay. So now, first, this is the agenda of this talk. So we first briefly introduce what is feedback control. This is the main topic is feedback control. Then we introduce two main topics: that's modeling, the learning of the models of the unknown factors, and then by using the learning results, we apply the learning-based motion control of the mobile robots. So first, what is control? Very briefly, so let me explain. The objective of control is to regulate and drive the target object or target system at will. So we can imagine many kinds of systems can be the control target. And now we focus on the mobile robot case. So this is a main target structure, feedback control. So let me briefly introduce. So there is a target system to be controlled, and it has some output, state, position, orientation, velocity, and so on. There is a target output. And so of course, there should be the reference, desired output. Then the feedback mechanism is very simple, just based on the deviation between the reference and the actual output. We apply the control input by the controller to the target system. This is the main target in this talk, okay? So then, let us give you some background. So for example, here is a quadcopter's position control case. So as you know, we have now many kinds of commercial quadcopters. Then, in this small toy robot, we can directly command the velocity input, not the acceleration, not the voltage. We can directly command the velocity. I mean, the target model is given by here. Just the time differentiation of the position is given by the velocity input. However, in real, if we just apply, this is experimental results, if we apply the constant velocity DC, the actual velocity response is given by here, big mismatch. So it says that, so we can send the velocity command. So between the actual velocity and velocity command, there must be the unknown dynamical system. Okay? There is a gap, existence of modeling error, unknown factors. So difference between the model and accuracy. So then we now consider the control techniques, some control techniques. If we know a priori the dynamical system, this dynamical system between the velocity command and velocity, if we completely know or successfully run this model, we can simply apply the inverse dynamics to achieve the desired velocity to be equal to the actual velocity. So next example is the control, feedback control. If we want to control the position to the desired position, then by using a simple feedback control, we can achieve the desired position, stability, or tracking. So then by using this control structure, so this works well for the constant desired position, but for the time varying desired position, so it doesn't work. So there is a steady state error. But so for such a case, we have another choice of the control. Combination of feedback and feed forward. So with feedback and feed forward, which has the inverse system of the reference, the desired position model, so we can achieve the good tracking performance, control performance, even for the time varying case. But if this system, the model of the reference is completely known or successfully learned, the final example is here. There in the real system, there must be the disturbance. But again, if we completely know the disturbance, if we successfully learn the disturbance, we can simply modify the control input, just canceling out the disturbance effect. So these are the background of today's target. And so we saw also the two showcases, background showcases. So what is the issue? So for example, let's consider the position control, the vertical position control. The system is here, model is here. We just apply the feedback control, proportional control. The initial position is 0.5 meter. The desired position is 1.5 meter. So then we apply the control input here. The simulation works well, of course, because we just simulate this model. But this is actual experimental data. So there should be the steady state error in real. There is a big gap between the model and the real. Okay? Another one. Let's consider the time varying reference case. For example, a simple case, the sinusoidal function, desired trajectory is a sinusoidal function. Then we just apply the 2 DOF control, feed back and feed forward. Then the simulation results here completely overlaps, works well, because this is just a simulation by using this simplified model. But here, this is actual experiment. The dashed line is the desired trajectory, and the solid line is the actual trajectory. You can see that there is an overshoot, there is a time delay. There is a big gap by using this model. Okay? So now, let me shift to the first main topic. Then let's try to run the model gap, this gap. Okay? So idea is very simple, very simple. So first target is the difference between the actual velocity and the velocity command. So we just suppose that there is an additional term, unknown gap, and we want to run this one by using the machine learning. The image of the block diagram here, real dynamic system, actual control input, but between the control reference. So there should be the unknown dynamics. This is a learning target in this case. So then we apply the nominal control, and we get the experimental data, training data. Then we have to formulate this delta. Now, in this case, this is a position control case, just a position control case. We suppose that the delta is a function of P, position, because position feedback is used. So, I mean, the choice of the explanatory variable is also the very important thing. What the delta is dependent of what, like that. So then this is a learning result. So we get the training data from the pre-experiment. So these dots are the real data, the sampled data. And this solid line is a learning result, function of P. Okay, so you can see that we almost successfully run as a function by the kernel method. So let me skip the details of kernel method. That's a learning method. Okay, the next one is interesting. Okay, let's consider the time varying case, sinusoidal function case. Then we apply just the nominal controller, to the off controller. Then it's interesting about the explanatory variables. If, similarly to the last case, if we just simply consider delta of P, we get this result. This is P and this is delta P. Then you can see that for each position, each value of the position, we have two choices. It's inappropriate. It's not function. It's not bad. It's not good. So now let's focus on this control structure. Then, the desired trajectory is based on the time, prior knowledge. So we consider the delta structure, delta of P and T. Then this is a running result. So this dots are the actual training data, and this curved plane is the running result. You can see that it fits the actual data. Okay, another one is a completely different situation. So let's consider the next. So far, we consider the unknown factors of the dynamic system. Next, we consider the controller. For example, in this case, human operation. For example, let's consider that there is a mobile robot and the human controlled by the telecommunication robot with a visual image, the desired position and robot current position, and we just control by using the user interface. Then, as you can easily guess, so the human has much uncertainty. So we apply another approach, Gaussian process regression as a kernel method. This is a probabilistic method. So here, this is the idea of the learning. So the humans, of course, humans operation control input is based on the deviation of reference and control output, desired position and the current position. So let's consider to learn the function of this, the function of the controller. And of course, as I said, because human has a much uncertainty, so we also explicitly consider the Gaussian noise. Then, just applying the Gaussian process regression, we get these kinds of the learning results. Here, this is the explanatory variable, the deviation between the actual position and the desired position, and this is the estimated result. Here, the solid line is expected value of the learning result. And in addition to that, thanks to the GPR in the probabilistic approach, so we get also the distribution information. This means implies the uncertainty in confidence of the results. Then we can see the interesting results. This is the result of the 5 trials. So this is the result of the 10 trials. We can see that all the size of the distribution, uncertainty is reduced. Maybe we can then have the hypothesis, maybe based on the experience by the human learning approach. Okay, another 6 minutes. Okay. So the final topic. So far, I introduced some learning target. Then by using these results, let's apply the learning-based control to improve the control performance. So this is a picture which I want to give you as a message, main message. Here, we consider simple feedback mechanism. But my message here, even if we delve into the simple feedback control, like here, many kinds of learning targets can be considered as a research or as an engineering subject. For example, let's see the case by case. So for example, learning target is dynamical system. Learning target is a controller. Learning target is a disturbance. Even for the reference, it can be the learning target. And also the external environment is learning target. We now just show some showcases of these learning target. The first one is, let's go back to the simple constant reference position control from the 0.5 meter to the 1.5 meters. We have already learned by the Gaussian kernel methods. So here, delta is learned. So let me denote the learning results is delta bar. Then the control algorithm is very, very simple. Just to cancel out, this is desired nominal control, and just to cancel out this learning result. Like here, block diagram. So just cancel out the learning result. Then the experimental result is given by here. So here, this is the desired target, and the dot line is without learning, as I showed first. And this solid line is our proposed approach. So you can see that the steady state error is improved, reduced. Very simple idea. So next one is sinusoidal function, sinusoidal time varying case. So PD control, we have already learned the delta. The same approach. We just cancel out the learning results. So here, because in this case, the delta is given by the function of t and position. So this can be done by here. So then this is the result. Here, the desired trajectory is the dashed line. And the dot line is nominal control, overshoot, and time delay. And the solid line is our proposed approach. No overshoot and less time delay. Yeah, very easy idea. Okay, then next one. Next one is newly considered a disturbance learning. Disturbance can be learning target. So let's consider again the learning process. There should be the counter window. Okay, then we apply the same technique, just the 2D controller for the trajectory just smoothly landing. For the nominal control, we consider the trajectory tracking controller, 2D controller, but so far, we have not run the applied the learning process yet. So then, first, we model the function of delta. So because in the landing situation, maybe, probably, so the disturbance is given by the height, position. So we consider the delta of P as the model of the learning target. Then this is a learning result, the P and delta P. And dots are the actual data, and so this smooth curve is a learning result. And this is the experimental results by using the learning-based control, the same technique, just to cancel out this learning effect. So then you can see that here dot line is without learning. It cannot run on the ground. And this solid line is learning-based control. It can run. And so then the dashed line almost overlapped by the solid line is desired trajectory. So you can see that not only for the landing process, but also the transient response is improved. Maybe the nonlinear dynamics of the robot is also learned by this technique. Not only here, but also here is improved. Okay, let us see again. So this is an experiment of this landing control. Oh, another 2 minutes. Yeah, you can see the smooth landing. Very simple idea. Okay, another 2 minutes. Okay, let me speed up. The final one, another one is reference. Okay, thank you very much. 1 minute additional, please. Okay, the reference can be also the target. For example, let's consider this case. Okay, I want to apply the tracking control, but the target is unknown. So for example, target tracking control for the unknown target. Then the approach is very simple. We just apply the feedback control with the feed-forward input based on the learning data. We just run by using the data of the trajectory of the target. I mean, this is unknown. But we run and we take the feed-forward term to cancel out this one. Then this is a learning result. This is a result, only sorry by simulation. Here, the dot line is the target motion, and the solid line is the robot motion. So by using without learning, it cannot successfully follow track the target. But by using the learning process, the similar approach, so we can see the more improved, more good performance of the tracking. Okay, final example is the external environment can be also learned. So completely different situations. So let's consider the operation of the mobile robot in unknown area. This is a true value, position and importance. For example, radiation level, pollution level, or heat level, like that, blah, blah, blah. So we don't know that this one, but we want to measure and estimate the importance of the field by using the limited number of the sampling data. Then the approach is here. Also with the probabilistic approach, we can get the average and mean value and the variance value in confidence value. Then the idea is very simple. The problem is to determine where is the next position to measure effectively, estimate the environment. Then very simple. Because the learning result distribution means the in confidence of learning, okay, then the largest value of distribution should be the next target. So this is a transient one. So this is a real value. Don't know in a priori. So 5 data, the estimation data, expected value, and distribution. We want to make this decrease, make it low, and we want to estimate this one to this one. Okay, then 14 data and 25 data, almost complete. So the objective is here. With a low number, small number of the sampling data, we effectively estimate the importance area. Then this is a final trajectory of this one. It's very intuitive. Far place, far place, far place, far place. Yeah, it's very reasonable position. So we can also consider the external environment learning. So because very simple introduction, I showcased. So this is an extension, one of the application of this technique. So for example, multi-agent robots, networked robots, so each of them runs the important area, and after running, they go to the deploy for the important area to environmental monitoring. Yeah, we can apply this kind of application. Okay, final slide. So anyway, so this is a big picture. So let me say again, even if we consider this very simple feedback structure, there are many learning targets. Maybe you can also look for, you can also find many learning targets in your own field. So that is my message. Okay, that's it. Thank you very much.
Thank you very much, Professor, for this nice talk. Is there any question in the audience?
Yeah, please.
The system of managing to control only the location, have you don't have the data set to give you this object which is located? So have you data set of things not only have to provide the location, but also to precise what's the thing which is located.
So what do you mean? What is the measurement value of this one? So at least the input value, first measurement value is the current position. So we suppose that each robot can know its own position by the GPS and so on. Then so at position, they measure something, pollution level or heat level or height level, like that, such sensor. And so in this case, so we also assume that there exists some noise, of course, because we are supposed to introduce a real sensor. We also suppose the existence of noise. But so far, because this is theoretical result, we just suppose, sorry, so far. So in this experiment, so I mean, the position can be measured by the motion capture system, but the actual measurement is a virtual measurement. We don't have any sensor in this experiment. Yes. Yeah, we assume that we have a kind of the data set of the measurement.
Any other question?
Slide 19.
19, okay. Sorry for my many slides.
No worries. I'm not an expert of the field.
Yeah.
I think I understand what is learning. But here you said that it's with a human experience.
Yes.
So compare human with artificial intelligence or the computer-assisted system. What is the most effective one?
Yeah. Good question. Yeah, good question. So to be honest, in this case, because we consider that only one task, the automatic way is much more preferable. But so we want to consider the human control in the future because human can detect some event. They can switch the control technology. It is very difficult to the automatic approach. So the big vision of this research is to identify the human model, but in more top hierarchy. Yeah.
The word experience for me here is really important because it's a large set of learning when you have behind the experience. For the human, it's a whole life with many stories. When it's about AI, it's limited to the data set.
Yeah.
So maybe
you're right.
Experience.
Yes.
It's higher level.
Yeah, as you said, because the data set is very limited. So even if we, for example, we create the learning-based control, it is just based on the current training data. Outside of them, no one, nothing.
Yes, exactly.
So the experience is very important. I agree with. Yeah. Thank you very much.
So if there is no any other question, we'll thank you again,
No.
Professor.
Matthew?
Oh, sorry.
Yeah.
Yes.
Just one quick question. Thank you, Tetsuya, again, for your presentation.
Yeah.
So maybe one quick question. In your experiments, you have used a simple-based controller. I mean, without learning, you used only a game controller.
Yeah. Exactly.
Do you think what if we had maybe, let's say, a better control, for example, a PI control.
Yes, 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 yes.
I think we would have, it would be interesting to use the learning method if we design better control.
Yeah, you noticed that. So because this is for the lecture, so
Yeah,
actually
sure, I guess.
for this one, so we use, sorry, let me shift this one. So we said that there is a steady state error, but PI control can overcome this one. But so, for example, but this case, unknown target case, this should be the, used, this should be the good for the learning target. So as you notice, we didn't use PI control for the easy of the understand.
Yes.
Yeah.
I was thinking the same. But
Yeah.
This is for the purpose of the lecture, and maybe for people who are not very familiar with control design, this method could be maybe easier to understand.
Yeah. But may I give you another comment, interesting comment? Sure. This means, here, this is a simple position, sorry. So we interpret that this simple control, so P control, and so this is just based on the, for example, delta. If we consider the linear function of this means just a gain tuning. We change the gain. Yeah, so we can interpret many kinds of the situation.
Adaptive.
Yeah, adaptive. It means sometimes. Yes.
I see.
Yeah.
ありがとう。
ありがとうございます。Okay, thank you so much. Long time.
Thank you.
Oh yes.
So have you explored adding the PID controller? Maybe we can reduce the steady state error by if we think that we can add a PID control on that. So can we reduce the steady state error by?
Yeah. As he said, so yeah, if we apply the PID control, we can really reduce PID. Steady state error actually, but we didn't do that in this case for the easy interpretation. Yeah, as you said. Yeah.
Any other question? So in this case, thank you very much.
Merci beaucoup.
And now for the last talk of the morning, we have Ludovic.